Okay, so I am going to talk about the phase transition of pure compound. And this is a chapter 4. Chapter 4 is essentially pure substance. And I think I can do it fairly quickly. And then we are going to move on to chapter 5, which is mixtures. And this is something that we are going to do. And when you think about the mixtures, there are different examples, something that I had to deal with. Eventually, I need to discuss about the phase diagram of the mixtures. So we are talking about, for example, binary mixture A and B. And that's an example for the following chapter. Current chapter, we are just talking about essential component A as it is. And this one itself, we are still talking about phase diagram. Okay. And then you remember that this is the Gibbs phase rule that I show you the degree of freedom, number of components minus number of phases plus 2. And the phase diagram, my usual choice there are different examples of phase diagram. For single component, I'm going to put pressure and the temperature in my y-axis and the temperature in my x-axis, and I'm going to draw it. And typically low temperature is a solid, high temperature is a gas or a vapor, and the liquid is somewhere in between. And then this is something that we are going to draw. And really the important part is now today I'm going to more focus on how we can understand, this is what they call the phase boundary. What the phase boundary is, and this is what I'm going to cover today. And last time I just talked about finishing up that, within this, I guess the domains of vapor phase, your degree of freedom is 2, because you can move temperature and the pressure independently. We are still in the vapor phase. Whereas at this point, when you're allowed to change it around to be in this, but once you change your temperature, pressure has to be changed accordingly to be locate yourself on the phase boundary. So these are the phase boundary. As you can see, this is a solid and liquid phase boundary. This is a liquid and the vapor phase boundary. And these are the topic that we're going to focus on today. And once you figure that out, it's not a big deal to understand the solid vapor phase boundaries. And so the understanding this phase boundary is your degree of freedom is F equal 1. Because you can still, in the phase boundary, you can move around. There's a 1 degree of freedom. Where the triple point is a 1, you have an F equals 0. And this is a fixed location that you have no degree of freedom in there. Okay, so this topic I am going to talk about is 4B, and then this is what is called the phase transition lines. And what I mean is, we want an expression for pressure change, temperature change. How do I understand this components here? Okay, so this is the one when you change it. This is when you change sort of the slope, right? So this slope is essentially pressure change when you change the temperature. That's what my choice on this. So this is an example that I'm going to focus on. And then where do I get my idea starting from is using this fundamental thermodynamic relationship based on the Gibbs free energy, and this is an equation that you guys can easily write once you understand the Bone square. And this is something that I'm going to rewrite it one more time, but this time I am going to write it as a GM, which is a molar Gibbs free energy. So now VdP minus SdT, and this will be a molar and the molar. So the reason that I'm doing this is because molar Gibbs free energy, which is going to be discussed in more detail in the mixture case, but this is essentially what we call chemical potential. Chemical potential has a meaning of Gibbs free energy change when you add a 1 mole of substance to the system and how much of the Gibbs free energy is changing. That's the definition of chemical potential. And this chemical potential is now related to this one. And I am going to, so this is the first one that we are going to say. So the mu is Gn for single component. And that's the focus for this chapter 4, which you will be finishing up. And you can easily recall your memory this change in the chemical potential when you change the pressure, keeping the temperature constant. Right, so remember what this one was before? That will be this one, right? I'm just changing the notation. So this is a Vn. And whereas this one is same thing. Chemical potential change when you change the temperature on the constant pressure is minus Sn. So that's a negative slope. This is a positive slope. When you apply the pressure, when you increase the temperature, and this is how those quantities are interrelated. So I am going to talk about once again, I think this idea was talked about before. Let's focus on the phase transition temperature argument based on the chemical potential. So I want to write it one more time here, which is number 2. So I said chemical potential change for any phases, any substance in the pure state is minus Sm. I think that we've been writing this equation for many times. Now I need to put some sort of the concept. Molar Gibbs free energy for solid, molar Gibbs free energy for liquid, molar Gibbs free energy for gas. Which one is the largest? Which one has the most highest disorderness in the arrangement of the molecule? Gas. Okay. Gas is the one most disorganized state. Solid, we are talking about some sort of crystalline form. They are on a sort of the lattice structures. Liquid is sort of you can have an average distance between the molecule can be defined, but it's kind of a little disordered state. So it is, and I mean I can even put a 1 there. This is a 1, but essentially this is the highest, this is the lowest. And then I am going to use the solid chemical potential, and then I'm going to talk about the chemical potential of a gas when you change the temperature. So there's nothing but just an easier way to demonstrate. This is the one that I drew before. I'm drawing again. So I'm going to draw the chemical potential as a function of temperature. What I know is this one has a mildest slope. This one is a steepest slope. Steepest, the highest changes when you change the temperature. So I'm going to draw here. That's a chemical potential for solid. Okay. And then I'm going to draw like this. That's a chemical potential for gas. And then if I draw something here, this is a chemical potential of liquid. And this is going to be the important topic for the mixtures and the property of the solution, which naturally involve the liquid property, and how this chemical potential is changes when you have a mixtures. And this is something that is going to discuss later. But in a very simple sense, you will have a 3 different slope, and this is a medium slope, And it does not say where this line is supposed to be. So now I'm going to draw the newer one. There is a possibility that I didn't violate any kinds of relationship shown up here. Once again, this must be a mu solid. This is a mu gas. And now this time, I'm going to say, well, it's a medium slope, but I'm relocating up there. This is a mu liquid. Okay. So for some scenarios with certain pressure, their chemical potential temperature dependence can be represented by this graph. In some cases like this. And why is that I'm drawing these two cases? And I'm looking for the one that is the lowest chemical potential. You see this? They are the one. Whereas here, I only see them the one. Right? So this is a case where you only see solid and the gas, right? And this is a temperature. What do you call this temperature? Sublimation. Right? So this is a sublimation as an example. Thermodynamics telling me that you cannot have gas in the low temperature and solid at the high temperature. Right? That one you are doomed to have this scenario. Solid at low temperature, gas at high temperature. But this is the one you are not seeing any liquid is way up there, so liquid cannot exist. And you see the sublimation as an example. Dry ice, right? Dry ice, you don't see that the solid become the gas without seeing it. But when you, even for dry ice, which is the CO2, when you apply the pressure, now you are seeing the solid at low, liquid in the middle, and the gas at the high temperature. And this is what we call, this is the fusion temperature, this is the boiling temperature, what somebody called vaporization temperature, somebody said melting temperature. Okay, so you are seeing these three phases together. So I can explain, I can explain that. How is that happening? Okay. So I can still keep this equation. And we are going to get in some really equation that I want to drive it to. So I use this equation now, right? So that's a use for the conceptual use for this. But now I haven't really used this equation, and this is going to be something that is going to be useful, as well as this one. I'm going to combine these two in this equation form for the construction of understanding the phase transition lines. So what that means is you have for example, solid chemical potential, liquid chemical potential is the same at that phase transition line. Right? So you're going to write these two equations, one for the solid, one for the liquid, and we'll start to work out that relationship. Okay, so this is now the important one. So let's talk about the phase boundaries. Once again, this is related to how pressure is changing when temperature is changing. So this is my pressure, this is a temperature. That's my choice for phase diagram. And I know that there is a phases that it could be a solid and it could be it will be a liquid. So that's a phase alpha, phase beta. This is a line, and I want to have an exact equation for this one. Right? So this is a phase that's a solid, and this is a phase that is liquid. What's going to happen at this phase boundary is when you change the mu A, U alpha, U beta. So that's what's happening along this line. When if you change your chemical potential this way, the following chemical potential has to be the same. So you're working along the phase boundary lines, and that's what my starting point. So that's where you have a same chemical potential for phase A and phase B. That's what happened in the boundary. If you go up there, this one wins. So chemical potential for alpha is lower than beta, so you only see alpha there. But at this location, at any location along this line, you have this kind of the balancing, the same chemical potential. Okay. And this is the same what I drew before. The same chemical potential, but now I'm going to use a differential form so that I can use the relationship that I just shown up here. Okay, the chemical potential change for any phases can be described by pressure change and temperature change, right? With the volume and the entropy goes up. So this is what you see here, right? So we are getting some. So I'm going to write Vm alpha dp minus Sm alpha dt. So that's for first one. Vm beta dp Sm beta. So that's where what's happening at that location where both phases has the same chemical potential. And I want to define the process that is a delta. So let's just assume that I want to see the transition from alpha to beta. Okay? So that's what I want to define. So what my definition here is delta Vm is Vm beta final minus alpha initial. Same thing here. Delta Sm for this transition line is Sm beta, Sm